why is this current response so particular? And exactly at this point, this image or this picture is an attempt to explain. If we consider our manganese dioxide or our manganese hydroxide or manganese oxyhydroxide, whatever, whether it's manganese 3 or manganese 4 surface, we have a huge number of manganese ion, and these manganese ions are more or less close to each other. If we start to oxidize, let's say, one manganese ion, this manganese ion oxidation will happen at whatever electrode potential. I don't care about the number right now. If I now try to oxidize the next manganese ion, the first already oxidized manganese ion, which is now as a manganese 4 ion present, might affect the energy I need to provide to remove the electron from the neighbor. If this interaction is very close, I will have a lot of difficulties to remove this next electron. So we talk about a strong electronic interaction between the first and the second and the third and so on until all the manganese ions are oxidized. That's the case shown here, strong interaction. If there is no interaction between the manganese ions, all manganese ions, in theory, we will not observe it, but in theory, all manganese ions will be oxidized at the same electrode potential. In that case of no interaction, we will observe indeed a very beautiful current peak. This idea was not at all new. This publication by Robin and Day was printed 1967 in a review based not on electrochemical observation but based on studies of organometallic compounds of transition metal complexes as studied with near-infrared spectroscopy. This classification of no interaction, strong interaction has been introduced by these two authors. Based on this approach, and going back to a discussion with Benjamin Kondratyev at St. Petersburg State University, I did a very simple calculation. Assuming such a strong interaction is effective, and assuming that the oxidation of the next ion removes only a tiny bit of higher energy, which means a tiny higher electrode oxidation potential, we can assign, in a very simple approach, we can assign a steadily growing oxidation potential to these manganese ions, starting from the first to the last. Of course, we are not talking about 1,000 manganese atoms, but we are talking about numbers like 10 to the 15 if you talk about the platinum surface. I don't know of any numbers how many manganese ions are there in the surface of manganese hydroxide or manganese dioxide of this particular chemical composition. So the oxidation potential shifts linearly, and if we now try to put this into mathematics, into a current response, into an amount of charge transferred, I tried first to use simulation program for cyclophotometry by assigning tiny current peaks to every single manganese ion. But there is no software which is capable of handling 10 to the 15 oxidation peaks. So I stopped after a very few peaks, and already after a very few peaks, in this very, very crude, very simple simulation, I got a response which certainly reminds you a little bit of those pictures you have seen before, for example, of the ruthenium oxide. And then I did an even cruder calculation. I just took a spreadsheet calculation. I calculated the amount of Faraday current, assuming this relationship, as far as the electrode potential is concerned, shown here. These are just numbers. These are not exactly electrode potentials I have recorded with a particular material. I added to the Faraday response, shown here as a dotted line, I added the double layer charging current, because this manganese dioxide, of course, also has a double layer capacitance, but the double layer capacitance is much smaller than this Faraday charge storage capability. I added up everything, and again, not very surprisingly, I get this very flat response. So this is just to attribute what Musgrave reported. This is his work, so to say, regarding the explanation of the difference between the behavior of alpha and beta manganese dioxide, but it helps us to understand why are some materials so good in storage and some are so poor, but it does not help, I just showed a single picture, it does not help to understand this current response. And so at this point, we can conclude, or at least we suggest in the publication, we suggest that the reason for this pseudo-capacitive behavior in materials like manganese dioxide is a strong electronic interaction between the ions, the manganese ions in this case, or the tin ions, or the ruthenium ions, or whatever ion, or whatever metal oxide, or sulfide, or whatever you are talking about. And this idea gains some support from observations like the response of manganese dioxide to a changing electron potential. The shape of the response depends on the status of hydration. So if there is a lot of water between the manganese species, the behavior is different as compared to a very dry material. And the water molecules in between the manganese species in such a layer of manganese hydroxide can be brought into connection, can be correlated with the response. So if the material is very dry, for whatever reason we have not yet understood, and we are now asking the theoreticians, the electronic interaction is not as effective. Whereas in the case of a hydrous material like the ruthenium hydroxide or the manganese oxide, the electronic interaction seems to be, for whatever reason, much more efficient and much more effective, resulting in this image which we saw last, this one, and resulting accordingly into this pseudo-capacitive current response. A totally different matter I wish to mention only in passing because it belongs into this image of current response of supercapacitor electrode materials is the behavior of intrinsically conducting polymers like polyaniline, polypyrrole, and so on. In that case, we have a totally different approach, but basically the same question can be asked: why is there such a huge current and only current peaks or current waves on top? And this is a very thin film. If we have much thicker film, we get current responses, which again are similar to the responses of these pseudo-capacitive materials. The reason for the behavior of the conducting polymer is totally different. Because in the conducting polymer, this is just a piece of a polyaniline chain, and this is the successive oxidation of the neutral state into the fully oxidized, into the semi-oxidized state, and this is the highly conducting state. In such a polymer, we have a wide variation of effective length of conjugation. So the oxidation potential of these various short and long units differ, and once again, the current response which you saw here is simply due to the fact that short units are oxidized last, and long units are oxidized first. So the explanation of this wide spread of oxidation potentials is totally different compared to the electronic interaction I talked about a minute ago. But again, we also can assume in such a conducting polymer electronic interaction between these segments of different lengths of conjugation, which might, this is the picture I just showed you, which also might explain to some extent why with growing thickness, this is a thick deposit, it's not just a very thin layer, like in the previous slide. The response also goes away from the pronounced peak shown here to a much broader peak-like appearance. So, in conclusion, the reason for this pseudo-capacitive behavior is in case of ionic species like metal oxide,